All right. Okay, hi everyone. Hello. So we are gonna go over the rules again. Like there's not very many of them, but you got to get used to them. So I think this is like probably the second to last time that I'm doing this, unless there's like more stuff in office hours. So okay, all variables in C are declared, meaning before you use them, you say what the type is. So for example, you say A is an integer and S is a char star and so on. So something like char star means address of char, something like int star means address of int, right? So that means that S is a number which happens to be the number of a cell in the memory table. Okay, PA, again, a number that happens to be an address. We initialize PA with address of A, which means that we say initially PA is going to happen to contain the address that's assigned to variable A. So S is a little bit more complicated. It's also an address. So it's an address of the first character of the string XYZ. We'll get today more into how XYZ is actually stored in memory. So R, the array, is a little bit more complicated. So we'll have to wait until Friday to get the details about arrays exactly. There are subtleties there, but basically anytime almost that you use R, what happens is it gets converted to the address of the first element. All right, so in the same way that PA, you can think of it as that's the address where the variable A is stored. R, when I use it, you can think of it as the address where the 4 is stored, the number 4. So, all right. Arrays, so I'll usually write it like that when I'm initializing. So optionally, inside the square brackets, you can say how many elements are going to be in the array. But if you're initializing, then it just automatically knows that you mean that it's an array of 2 integers because you gave it 2 integers. So in more detail, so ampersand A, so address of sign, means the address where A is stored. Star PA is the value at the address PA. So again, important to see the difference between int star PA over here and star PA over here. Those are conceptually related, but in a way completely separate, right? So int star is a type in the same way that int is a type, in the same way that just char is a type, and so on. So the way you read it is int star, and then the name of the variable is PA. Yes.
Is there a good reason there's a space in
well, so I think there's some talk on Discord about that as well. Or at least like I saw some this morning. So basically it's a matter of style. I just decided that we're following Kernighan and Ritchie style, in part just because Brian Kernighan is from like U of T Yangsai. Like also like you'll see it both ways. So the argument that's being made here is like, if int star is a type, why don't you write int star space PA? Wouldn't that be clearer? And the answer is, well, arguably yes.
You can do that.
You can. Okay. Yeah. So the answer is, as far as C is concerned, it's the same. It's just that, like, there is multiple conventions. People do different things. I decided we're going with Kernighan and Ritchie style. They're like, Paul, one of the TAs, made a strong argument last year, in fact, about, well, like this is confusing. Yeah, for int star space. And like my counter argument, okay, like you're gonna see it both ways. It's like 30 seconds to clear up the confusion. Well, we spent like 120 seconds now. But like after that, like it honestly shouldn't matter. So yeah. And also, in a way, kind of being confused early is good because now that we've cleared it up, hopefully it's all fine, and you will see code that looks both ways. So, okay. So star R, remember, R gets converted into the address of 4 anyway. So that means that star R is just 4 because R gets converted into the address of the first element of the array. So star R is just the first element, which is 4. Make sense? Questions? Okay. So that's what happens within the function. So now what happens if you call a function? So just like in Python, variables are local, right? So the int a, that's a parameter to f, that's a local variable. What happens when you call a function with a value? So for example, you say f43, is the 43 gets copied into a. So a is of course separate from the 43. The reason I put a 43 there rather than a variable name is that, well, nobody would think that you're modifying the number 43 when you say a equals 42. 43 is still 43. It works exactly the same way if the argument is not a literal, so 43 is a literal because we're inputting data directly into the program. If it's a variable, it's the same. It doesn't matter, you're just sending the value, you're not sending the actual variable. Right, so what's going to happen is that 43 is going to get copied into a, and then the local variable a becomes 42. It's local, calling f has no effect. Make sense? Exactly the same thing. Nothing is different about this slide than the previous slide, except that now the type that we're sending is in star. Right? So the function f now takes a variable of type int star, and then it sets the local variable PA to 0. It's a local variable. Doesn't matter that it happens to be an address. It used to be when we're initially sending address of A to F. Initially, the value of PA happens to be the address of this variable A. And then we say, okay, now it's going to be 0. Fine, the local variable PA used to be the address of A, and now it's 0. A does not care. So the same process here, but a different effect. So the change here is instead of saying PA equals 0, we're saying star PA equals 0. So what I'm doing here is I'm saying I'll send F the address of A, and then F is going to go to that address and change the value at that address to 0. Right? So the process is the same. So I'm writing you a letter. Go to BAN 2028, my office if you've never been, and leave a cookie there. Okay? You don't change my letter. You get my letter with my office number. You go to my office, you change the office. The letter, like what I wrote though, like I wrote down BA 2028, you cannot change that. You can go to BA 2028 and change the value of BA 2028. All right, but it's important to see that the process is still the same. We are still saying, take the value here, which happens to be the address of A, so the address where the variable A is stored, and we're sending this address, so it's a number, some address. We're sending it to F, so we're copying this guy into the variable PA. And then it happens that we say to the function, go to that address and change the value there. Yes.
So the last two functions we looked at were like to demonstrate that appointments, right? Like they don't do anything. The previous two that you showed us,
They don't do
this
anything.
one, another
Yeah.
one, just to show that doing this doesn't happen.
Yes.
All right, okay.
Yes, that's correct. So so this one and this one, they don't have any effects outside the function. This one does have an effect outside the function. It's not because they're structurally different. They're structurally exactly the same. In every situation, you are sending a value to the function f. It's just that this example, the function f gets a value which happens to be an address, and then it goes and changes the value at that address. Right? So that's the difference. Structurally, though, they're the same. So it's very uniform in C in the same way that it's uniform in Python. Yes.
When you call a function to a variable that has, like, for example, a, do you have to put that in there?
Well, yes. So here, if you say f of a, instead of saying f of address of a, what's going to happen is, first of all, you're going to get either a warning or an error, depending on the type of A, because it has to be that the type of this value matches this type. So if you're sending it an integer, but it expects an int star, it's going to at least give you a warning saying, hey, like I was expecting an address and you're giving me a plain integer. Separately, if you force it, which you could in this case, if you force it to run, then what it's going to try to do is go to address 45, which very likely just makes no sense, and try to modify address 45. Now, on most computers, so like if you buy whatever you have, like you usually have like 8 gig of RAM or something, right? So 8 gig of RAM means that you have 8 gigabytes of memory. It's usually the case that like one address is 1 byte, so you have 8 billion potential addresses. And usually the very small addresses are actually like not accessible. You're not allowed to go there. On a modern computer, that's not like a rule. So if you have like whatever, like something like a very small device, whatever, it might work a little bit differently. On the laptop, what's gonna usually, like with the usual operating system, what's gonna happen is you're not allowed to access like an arbitrary address. You have a block of addresses that you are allowed to access. The operating system, so for example, Windows or OS 10 or Linux is going to tell the program when it's running, this is the block of addresses that you're allowed to access. And 45 is usually not going to be one of those addresses. It's even more complicated than that, in the sense that the address that a modern program written in C is going to try to access is not actually like a real address in the hardware. It's like a virtual address that the operating system maps to the hardware later on. So that's something that you'll get into like in third year if you take the operating systems course, and maybe not even then. It's complicated. Part of why it's complicated. You might remember, I think it's not an issue anymore, but you might remember like 10 years ago, 15 years ago, that you would be very young. 15 years ago, you wouldn't remember. But it used to be the case that if you ran a lot, in fact, it's still the case. If you have like a lot of tabs, your computer slows down. Part of the reason that it slows down sometimes is that you run out of the memory that you can access fast. So all the tabs, whatever that you have open in the browser, each of them has like variables and stuff, and you run out of space. At which point what happens is the operating system kind of pretends that the hard drive is also your random access memory, is also the fast memory, and it just automatically maps when you're trying to access something far away. It maps it to the hard drive, which is slower to access. So this is one of the reasons that things slow down sometimes when you have a lot of programs open. It's less of an issue now. So it's not usually the case on a modern laptop that would be the situation, but sometimes that as well. All of that is hidden from you ordinarily when you're writing in C in ESC190. In ESC190, what happens is you just, behind the scenes, the program gets allocated some block of memory, and the operating system takes care of pretending that that block of memory is actually in the hardware rather than like in the pretend hardware. And then like when you say int a equals 45 in your function somewhere, well, it decides, okay, a is going to live at this address, and the operating system is going to take care basically of what address exactly. So all of that was kind of hand waving at what's actually going on. What we think is going on when we're programming, at least right now, is we say int a equals 45. Well, the computer is going to decide that a lives at some address, and then address of a is going to be that address. That's all we need to know. Okay, make sense? All right. So, all right. So the next thing we got to talk about is blocks of values. So I say blocks of values rather than arrays because it's not just arrays. So we saw so far two different things that are stored as blocks of values. So one is strings. Why is my screen sharing paused? Hold on. Oh, resume. Okay. So one thing that was stored in the block is a string. So for example, if you input a string literal like hi in double quotes, what's going to happen is the computer is going to decide, okay, I'm going to store this, for example, starting at address 1032. And then the H is going to live in 1032, and the I is going to live in 1033. And then we have to have a null that signifies that we are at the end of the string. So it's going to get stored like that. Of course, 1032 is arbitrary. If you have something like an array, so here I have a way to initialize an array of two elements that are 3, 4. So I can say that the 3 lives at address 2064. And then one issue that, again, we have to defer the complete discussion of is that different types of values take different amounts of storage. So in this case, 32 is a bit much. So in this case, an integer would usually on most computers take four memory cells, essentially. All right. So 3 is going to get stored at, for example, 2064 and 2065 and 2066 and 2067. And then 4 is going to get stored at 2064 plus 4. All right. So we'll later see how it is that those things are stored. We haven't seen it yet. For now, it's just that different types of values take different amounts of space. We mentioned briefly when we discussed floats in Python that they store a limited number of digits. So basically, 4 cells in the memory table is ordinarily how much an integer would take up. This has consequences for how many digits you get to store in an integer. Similarly, a car takes 1 memory cell. So for that reason, there aren't a lot of different characters that you can store. Of course, again, as a preview, I'm not going to get into details about that. Of course, kind of there's, tens of thousands of different characters that you can actually input on your computer. Those would not be able to get stored in the car because there's not enough space in one memory cell. Yes.
Can you still access in the array? Can you still access the value 4 as like?
Yes. Next slide. So, well, not next slide, but like slide 23 or something. Yeah. So that's coming. Sorry. So the next thing is what's called pointer arithmetic. So arithmetic referring to like the usual thing where like 2 plus 5, whatever. So same thing, but with pointers. Remember, pointers are just addresses, right? So if you're doing things like this, so if you're saying S is the string high, so that means that S is the address of the H. You can say something like S plus 1. And S plus 1, if H is at address 1032, well, S plus 1 is going to be 1033. And then star S plus 1, what is it? Well, it's go to address 1033 and get me the value that lives there. What's the value that lives there? Well, 1030, I, right? So you can do it like that. If you're doing something like this, so let's say that you have an array and the array is 3, 4. This again is copy pasted. So here you have the value 3 and here you have the value 4 at address 2068. So array plus 1, because array is of type int, that's going to be 2068. So basically array plus 1, that's the distinction between like arithmetic and pointer arithmetic. It looks at array and it says, oh, it's an address of an integer. An integer takes 4 cells. So that means that array plus 1 is actually going to be 2064 plus 4, not 2064 plus 1. So that's as opposed to S plus 1, because S is an address of a car takes 1 space. So I realized that you've just found out that car takes 1 space, that's universal. Int takes 4 spaces, that's not actually, well, that's in practice universal, but not set in stone. Like not, you might imagine that like on some kind of weird exotic hardware that wouldn't be the case. Basically what we need to know is star R plus 1 means get me the next element in this block of values. If each value takes 4 memory cells, that means that R plus 1 is actually plus 4. If the values take 1 memory cell each, then R plus 1 is actually going to be like an actual R plus 1. Does that make sense? So, okay, so that's pointer arithmetic. So the last thing is the access an element of an array. So in fact, what happens when we use this notation in C is it just converts it to star array plus 5. So when you run a compiler, the compiler basically does a search and replace kind of deal and replaces anything that's like array at 5 to star array plus 5. That's what happens. So this is kind of like a fiction. So this kind of fiction is sometimes called syntactic sugar. So like something that you can use to sweeten the code, just because like this is the same as what's actually going on, which is this. And the compiler is just nice enough to sweeten the code, well, to let you sweeten the code, I suppose. And then it makes things more complicated before it actually gets converted to machine code. So this is as distinct from actual new syntax, right? So for example, in Python, doing something like L at 3, that's not the same as that. Like that involves actually complicated things, going to the Python list, which is actually more complicated, right? Because a Python list can have different types of values, some of which can take a lot of space, and then going and retrieving the value. So that actually does something substantive. Whereas this, like, it's kind of adding a new thing to C on top of this, but it's not adding anything substantively new. So there is like a less used term, which is like syntactic salt. Some people prefer salt to sugar, but the idea, or both, whatever. But the idea is syntactic salt is something that's added to the syntax that constrain what can be said, right? So an example would be, well, technically you could maybe say, well, maybe I don't need, so semicolons are not exactly syntactic salt. We haven't really done stuff that can yet be said to be that exactly, but something like semicolons, which if you are used to Python and you're like writing in C, I certainly have this experience. If I've like spent like months writing in Python and then I have to write something in C, I forget semicolons all the time. In a way, semicolons are necessary, so they're not quite syntactic salt, but it's like something that constrains you so that you're forced to write good code, as opposed to sugar, which lets you write something nicer that converts into something more gnarly. All right. So that's like that. So questions about anything? All right, let's do more examples. So I'll go to it's stuck. So this is linked on Piazza. So I'll just go and I'll do a few more of those deals. So we stop here, right? So this is linked on Piazza. I think clearly people do have access because I see. Yeah. Okay. Hi, Dinosaur. Hi, Cheetah. Okay. So, all right. So yeah, let's do this. So first of all, what happens when you run main? Well, the first thing that happens is the program pre-decides where everything is going to be, right? So it might decide that A lives over here. And here it sees that there is 3 spaces there. So here, like, there is a trade-off between kind of sticking close to reality and being concise. So I'll put A1 at 1034. Usually it's 4 addresses, but I'll say that A1 is going to live here, and I'll say that A2 is going to live here. And then there is also a P. So I'll say that P is going to live here. And that's that for now. So we are running main. So A is initialized to 5, 6, 7. In fact, initializations usually are going to rerun, but not necessarily. So this is going to be 5, and this is going to be 6, and this is going to be 7. So now we're saying n star P is equal to A. Actually meant, it is A. Yeah, so n star P is equal to A. So A gets converted to the address of the 5. So that means that the value of P is going to be 1032. And now we're saying f of A. So f is about to run. F has a parameter, which is a local variable. So maybe it lives here. And we're saying f of A, so A, the address of the 5, gets copied to the local A. So that means that 1032 gets copied to local A. Right? Because A is the address of the first element. It gets converted. So now inside F, we're saying A at 0 is equal to 7. So that means go to the address 1032, don't skip any cells because we're saying A at 0, and make it be 7. So when we print, so when we're done, this goes away. So you can think about it as disappearing. But A at 0 was already changed. So that will print 7. So you can think of it as being analogous to what's happening in Python, in the sense that if in Python, you write something like this, and then if you have a main function and you define L and you do f of L, that's going to change L as well. Right? But the mechanisms are not quite the same here. So in Python, it's always the case that when you call a function, you send, you copy the variable table value. So you copy the address that's used here to the address that's used here. In C, it's not always the case. It just happens that in C, specifically with arrays, an analogous thing happens, which is if you write it like this, where you say f of A, the address of the first element gets copied. And then here we're saying, go to that address and change the value. Right? Yeah.
Main block says into 0 into 6, but did that actually get negated by the 5?
Oh, sorry, I didn't, well, not necessarily negated, but thank you, I skipped it. So it used to be 5, and then it became 6, and then it became 7. Thank you. Yeah.
And when you put f of A, doesn't it have to be doesn't it have to be star A?
No. So A is an array, right? So when you use A in code, except in one circumstance, which we haven't seen, it gets converted to the address of the first element. So one common thing that people try to do is and I kind of intentionally didn't write it like that, is they try to write something like this. That will work. It's just that it's exactly equivalent to saying in star. So again, kind of syntactic sugar. See, in this case, it's not sugar, it's like MSG, something that not everyone likes. So it's kind of saying, oh, like it's an array, fine, trust me, except it's not an array, it's actually just an address. Now, we haven't yet seen situations where this makes a difference. There is one situation where it does make a difference, but this is not, like, this is just syntactic sugar. This is just in starting. It's not an array. You cannot pretend that it's an array. Yes.
Is it better practice to stick with what you started with?
I
Will that kind of keep us from?
Well, I think there is arguments both ways. So like the argument for doing it again. So let me do it now. I guess I actually have some time left over now. So the difference is if annotations. Oh, because it thinks it's Python. So the difference is like this. If you write things like so, then you can use size of array, and that's gonna be 12, and that's the total number of memory cells occupied by array, or just R. And that gives you so you can say size of array divided by size of array at 0, and that would give you the number of elements in the array. So this, I cannot exactly explain how it works, but that gives you like how many cells does array at 0 take up? And then, well, how many elements? Well, the total number of cells divided by the number of elements that one cell takes up. The number of cells, sorry, one element takes up. That's the number of elements. So this would be 3. Right, 12 divided by 3. So you can do it with an array. You cannot do it with an address. The address, so if you say, so size of PA0 is, yes, usually would be 8. So absolutely not the number of elements in the array times 4. This is the number of memory cells occupied by an address. And in the function, there's just no way that you can get this information using size of. This is like an extremely common bug where people do this and it doesn't work. So getting back to your question, is it better to write it as like this or like this? Well, I would say if you're worried about doing size of A by mistake and thinking that it's the number of elements when it's actually not, then it's better to write it as in star. On the other hand, if you're worried about the program being clear on the fact that you don't just mean an address, you actually mean an address of a block of events, then arguably kind of the square brackets give you this idea faster. So there is a trade-off.
How does because the strings we have the null, The null type at the
Yeah,
very end?
yeah,
How do the-
yeah.
how do the arrays?
It doesn't. So if you need to know how many elements, you need to separately say. So usually if it's an array, you would say like in size or something.
Yeah, you have to do that.
Yes. Yes.
One more question about the difference between the address and an array.
Yeah.
Could you write P_A brackets 0,
Yes.
and that's still the
Yes.
value?
Yes.
Okay.
Yes. So this is exactly the same, right? So saying P_A0 at 0 is exactly the same as P_A0 at 0 because it's the same as star P_A0 plus 0. Though this just gets converted. It's exactly the same. All right. So that's like that. So part of this is that like arrays are not super convenient to use. So arrays in C are fixed size, so you cannot append to an array or anything like that. It's fixed size. When you pass it to a function, well, it gets converted to the address of the first element, so you lose information about how large it was. So why is it also inconvenient? Well, it's because when C was being designed, the concern was not convenience to ESC190 students. It was about like getting things to run in a reasonable amount of time back when computers were slow. It's still the case that if you're writing something that's supposed to run very fast, like, for example, an operating system where, you know, there's a lot of things going on, you want everything to be as efficient as possible. Or if you're writing something on like really cheap, really efficiently made hardware where, you know, it's slow because it's cheap, again, you might like to optimize for speed. Those things. So sometimes those trade-offs don't exactly make sense in modern time. Like you have a large array, like wouldn't it be convenient to also pass the size automatically the way it's passed, the way you can find out the length of a list in Python? Yeah, like arguably it would be. It's just that that's not how C is designed. And the choice is always between moving to a new language completely so that all the old code that you have is useless. You have to the word people use is port to kind of translate basically the entirety of your code base to a new language, which might be more convenient. Or do you keep your old code base with all the inconvenience that it implies? So C is still kind of the fastest, but there are modern languages which enable you to run things fast, but are also more convenient and more safe. So by safe, I mean here, like if I say A at 0 equals 7, and actually it happens that A is not a valid address, the program would just crash. That's one way in which it's unsafe. Another way in which it's unsafe is on modern operating systems, that's less relevant, but if you go and like in C, you can just say, I want to go to address 5 billion and see what's there. Well, that's a way to steal data from the user, because if the user stored something important at address 5 billion, you really don't want the program to be able to just go there and like take your password or whatever. So less of it, that's been fixed on modern operating systems anyway, but C, because like C, instead of checking, hey, like, are you actually allowed to go to address 5 billion? It just says no, like, got to go and get the stuff at address 5 billion. We're in a hurry. So that's the trade-off. All right. Other questions? I don't think we have time for another example, so I'll see you tomorrow. Bye.
For example, OpenAI, if they're trying to like maximize their compute, would you speculate that they're using C or C++, or are you think that's even too low for them? As
So,
far as I know, they're really trying to push with whatever hardware they have. It's
yeah.
max it out.
Yeah, well, so basically what you do is, so I don't know what OpenAI is doing currently in secret. So basically what you generally would prefer to do is you would prefer to write code that interacts with our hardware, possibly even in assembly.
Okay.
But then this would be kind of packaged and then you pull that, I would imagine. So with OpenAI, I don't nobody knows. Ilya Sutskever, the chief scientist from OpenAI, used to be at Toronto.
Yeah,
And I
I think
happened to-
Andre Carpenthy also did.
He's undergrad, yeah. I didn't, so like actually like, so Ilya, I do know. Andre, I never met for some reason, even though we're like the same age. So he's more successful. So what Ilya had done here, well, so Ilya and Alex Rudavsky, Alex has written the kind of interaction with the GPU in like part assembly parts. And
Part assembly?
yeah, yeah. So that was back when, so now the interaction with the GPU comes standard from NVIDIA. So you don't need to, but it didn't use it. So yeah, so that was assembly in C, I believe. And then now kind of for standard GPUs, NVIDIA does all your work for you. With whatever custom hardware they have, yeah, like it's got to be that some of it is assembly in C. I imagine that.
Thanks.
Yeah.
I heard that it's like 4 blocks.
Yes.
But when I want to access the second element, where it might just use like the I just thought the plus 1. Yeah, 274. Like why is that?
Because A is a type in star, so C knows that if A is in star, then that's a +4. Yeah.
And like, can I declare and let's go. Taking that up like this.
No. You can say like int star B equals A. So this is just because like on the right hand side it's an array, so it's got to be that on the left hand side is also an array. Yeah.
I had a question. How is this one different? This one isn't it? Same thing. This is one. Right?
Well, no, because PA0 is an address of an integer. So the PA0 is a type in star, and then array R is an array of integers. So that's the one difference between, so that was the one difference between arrays and pointers, right? So when it's an array, size off makes a difference, whether it's an array or whether it's a pointer. That was like the one difference. Yeah.
Yes.
Yeah.
So when you did size of the array, like
Yes.
how did you know it was 12? Like
Because 4 times 3.
so it's basically the first element in the array.
Well, I mean, all the elements of the arrays are integer, and I happen to know that on my computer, on yours as well, although that's not guaranteed, integers take up 4 cells.
Oh. Okay. Okay. Thank you.
So I tried implementing the 2 functions, one with Instari.
Yeah, well, so that's like the difference is like you cannot call size off. Instead. Or like you can, but it's going to give you the size of A, which is 8. So that's going to
For
be
this.
Yeah, so that's going to be I imagine 2 is what it is. Yes,
So these should both compile to this,
which
like
they
output this.
which they did. Yeah.
Okay.
Yeah.
So both the size of A in both of these cases.
Yeah, because
that's
this
the
is
number
just
that's-
syntactic sugar.
Okay.
I understand when we do the string, like using the address +1,
Yes.
because 1 is the like 1 out 1.
Right. Yeah, 1 cell.
Yeah.
Yeah.
But for here, like why should we +4? Because this is the address and plus the
Well, because this is an address of an integer, and on most computers, integers take up 4 cells.
Yeah.
So if on the computer that it runs on, it takes up 4 cells, then like that's the rules for pointer arithmetic.
Mhm.
Is +1 actually means go to the
Next.
next element, not just add 1 to the number.
Yeah,
So
because,
that
yeah,
the difference between like numbers and pointers.
so ARR is the address of the, right?
Yes,
Like, it's always find to the first element of the array. But
right.
0.1, like, to the name of the array always means to the next step.
It means like pretend that it's an array, which it's not necessarily, right? It might be just an address of an integer and there's nothing after that integer. But it says pretend it's an array and go to the address of the next element.
Yeah, because for the int, we already, like, declare here.
Yeah.
Why is +1 or +4 at here?
Because array is of type address of integer.
Array is type of integer,
Address of
address
integer.
of integer.
Yeah, and then it knows that like adding, so here's another way of putting it. Adding 1 to an address of integer means adding 4 to the address.
So if we directly add to the name of the address,
What do you mean by name of the, like the name of the address is R.
ARR,
Yeah, that is already the name of the address.
because ARR is 20464, right?
Yes. What,
So-
that's the value, and then the name
That's
is
the
R.
value.
Yeah,
So why, like, mathematically, ARR equals to 064 and
That's right.
1 doesn't equals 4, so it's like,
well, yes, and that's the difference. That's why it says pointer arithmetic rather than just arithmetic,
Okay.
right? So because R is a pointer,
Yeah.
so it's an address, it's basically the address of this guy, of the 3.
Okay.
Then when you say add 1 to the pointer,
yes.
that actually means get the address of the next element in the block. It doesn't mean literally add 1 to the number.
So 1 here means we identify the type of ARR, the address, the type of in that address,
Yes,
and 1 it will be the unit of that side of.
you could say that, yeah.
Or so pointer is not equals to address, it's just like
It
point
does,
to the
no, a pointer is an address.
Okay,
So it's just that adding 1 to a pointer is not the same as adding 1 to a number.
okay, yeah, thank you.
Yeah.